So today we are going to continue this module of graphs and graph traversals. And so now that sort of the first third of the course is over, the course is going to develop faster. We are going to cover I would say many more interesting topics. We will often develop algorithms that combine ideas that we have learned in the past. We will use these notions of graphs and graph traversals extensively. And as I think as how we design software of any kind or algorithms of any kind, we just build algorithms out of other algorithms, and we don't have to look inside. Once we know how to do median selection, once we know how to do sorting, once we know how to do closest pair, we don't need to look inside that algorithm as to how it works, as long as we understand what it does, what its output is, how long its running time is. Okay, so today we will start off by trying to understand this structure of trees, which I think we talked about binary search trees, heaps arranged as binary trees, and so on. So we know what it means, but we'll try to formalize that a little bit more. Then we will talk about two traversals. Most of the time, we might just restrict to breadth first search, and towards the end, we'll talk about breadth first search. Okay. Reminder: the midterm is today, the evening, at 6:15 p.m. The location has been sent out on Piazza. I don't want to repeat it, lest I make a mistake. I was hoping to return quiz 1 to you today, but it's not yet done, so I didn't want to hurry the TAs to finish it, but you'll definitely get quiz 1 grades back by over this weekend, and you'll get your quiz 1 back by this week. Okay? And the other things are being graded as we go. Any questions about the midterm or anything else before we start talking about it?
I'm just worried because I'll get out, but that's fine.
Yes.
So you said in class last week that the midterm, the level of difficulty might be toward the quiz, but on Piazza I saw some, like one of the instructors that the level of difficulty might be closer to like 4. So I just wanted to like make sure.
So I corrected that statement, if you remember. Yeah. Yes. So
it'll be closer to like the quiz and the sample.
that's true. It will be close. But yeah, it's very, of course, as you can, I've taught this course many times, so you will assume that I know sort of the method to it, but that's not the case. I make mistakes, many mistakes, and misjudge often. So I would say the quiz and the practice problems are more representative of how the exam would look like than your problem set. Having said that, one question could be more difficult than what you might have seen before, and so on. The one thing I would emphasize is I think there will be clear instructions when you need to give proofs, when you don't need to give proofs, and things like that. Because I think this is the limited time setting, so we completely understand. So there will be more clarity on when you have to justify something, when you just have to return your algorithm without much justification. Okay. Any other questions? Okay. So let's define what a tree is, okay? Because this is going to come up many times. And for most of the class, let's assume for the entire duration of the class until some point here, we are going to focus our attention on undirected graphs. Okay. All right. So, what is a tree, and how do you define a tree? Yeah.
Those groups inside the.
Okay, so let me try to define it. A tree is a graph with no cycle. We understand what it means, what a cycle means. What is a cycle? How do you define a cycle? If I write it formally, a cycle is a sequence of vertices. X1, we say V1, V2, V3, Vk, such that what holds? There is an edge between V1 and V2. There is an edge between V2 and V3, and so on, and Vk minus 1 and Vk, and Vk and V1. Okay? So such that V1, V2, V2, V3, dot, Vk minus 1 Vk, and then Vk, V1, all belong to E. Okay, remember our graph is represented as a set of vertices and edges. E is the set of edges. Okay? You have to add one caveat, we have to be careful about this. A cycle, there's something wrong with this statement, some sort of minor technical issues with this statement. Can somebody point this out? Okay, it's an undirected graph. Pardon? Something wrong about it. If I just say this, we are calling things as cycles which are actually not cycles. So let's take k equals 2. You have just two edges, V1, V2. And you have two vertices and there is an edge between them. Is that a cycle? No. So k has to be at least 3. Okay, otherwise the cycle has to have at least 3 vertices. We are not allowing multiple copies of an edge. If you allow multiple copies of an edge, then you can imagine you could call this as a cycle. This is indeed a cycle, but we are not allowing 2 edges going between same 2 vertices. Okay, so k has to be at least 3. Okay. Now it's important to understand how to write something like this, even though we won't be constantly writing this. Okay, because it will be just too much of a pain. So often when we talk about cycles, you will draw a picture. Oh, this is a cycle. Okay? Good. Now, there is a problem with this statement also. I've defined a tree as a graph with no cycles. Connected graph. Okay? Because a trivial example of a graph with no cycles is this graph. This is a graph that has no edges. It's an empty graph. Of course, it has no cycles. But is that a tree? No, it's not. So a tree is a connected graph with no cycles. That's a complete definition of a tree. Okay. So the first thing we're going to try to prove, first observation, it's an observation, but it's good to go over the proof of it. A tree over n vertices has exactly n minus 1 edges. Okay. Okay. Okay, so let's try proving this. How would we go about proving it? Yeah.
Could you do like a proof by contradiction and then talk about, let's say it has n edges?
Okay.
Say it doesn't support.
That's a great suggestion. Okay. Well, it could have fewer than n edges also.
Yeah.
So you'll have to try to check whether it has fewer than n edges or
Or it has less than n edges, wouldn't it be unconnected? N minus 1 edges wouldn't have fewer
Ah.
edges.
it will likely be unconnected, but we'll have to prove it that it's not connected.
Cases.
Yes. Okay. Okay, good. So one attempt will be by contradiction. So you could prove if it is less than n minus 1 edges, then you prove that not connected. Greater than n minus 1 edges, you prove that it has a cycle. Okay. Okay, that's one idea. Any other?
Induction probably.
The other option is to prove using induction. Let's try proving using induction. Using this also, we can give a proof, but let's try to prove it by induction. So the base case, what I guess the simplest base case is if n equals 1. So if n equals, if there's only one vertex, what does your tree look like? Just the vertex itself. There are no edges. Okay? So there is only one graph over one vertex. Right? That's the graph. And it's a tree because it has no cycles. Of course, it's connected because there is only one vertex. How many edges does it have? 0. So n minus 1 equals to 0. Okay? Let's consider induction step. So assume a tree over n vertices assume a tree over n vertices has n minus 1 edges. Okay, we will prove tree over n plus 1 vertices has n edges. Okay? Okay, how do we go about proving this? Yeah?
Out of those n plus 1 vertices, n are already connected, and we just have one disconnected vertices, and we can connect it.
No. So what you're given is you're given a tree over n plus 1 vertices. So it's already connected. Okay, so let's see. This is what you have to prove. What does this mean? Somebody has given you a graph G, which is a tree. This has n plus 1 vertices. And it is connected. And it has no cycles. Okay? It's connected. No cycles. Your goal is to prove that this has exactly n edges. Is the question clear? What you're given is a tree, is a graph which has n plus 1 vertices, it's connected, it has no cycles. Your goal is to prove that it has exactly n edges. Yeah?
We can say, since it is already C, we assume that for if we have n edges, n vertices, it will have n minus 1 edges. So we can split n plus 1 as n and 1. and since it's connected, the one node will always be connected to the
Uh,
and we can say it is
not clear. How do you split it into? So this is the picture looks like. How are you splitting into n and 1? Can I take this to be my one node? See, somebody else not. Yeah.
I guess my strategy would be to look at, you already have a tree with no cycles.
Yeah.
So just add one and try to,
Well, that is not, no, that's good,
No.
that's a good, it's a good try to go from here, to try to go from here to here. But notice that, how are you sure that if you start from here, you are considering all possible trees over n plus 1 vertices? This is what you have to prove. So essentially what you're given is a tree with n plus 1 vertices. If you're trying to prove for what you're trying to prove, you can try to reduce it to what you know. But you cannot start from what you know to construct something because you're not sure you've built the thing that you were asked. Okay, so you have to be very careful going from here to here. I mean, it's possible in some situations, but you have to be careful. Okay. So this is what you're given. You're given a tree with n plus 1 vertices. It is connected, it has no cycles. You would like to use, and you have to prove that it has n edges. You would like to use the fact that a tree over n vertices has n minus 1 edges. But this is not a tree over n vertices. This is a tree over n plus 1 vertices. Yes?
Could we say something about the fact that all of the, I guess, the leaves
Yeah,
where it terminates only have one edge extending?
good.
Could we
So,
extend from-
so you could try to do the following. You could say, okay, let's look at this picture. You could say, oh, let me remove this. Okay, this was the same idea, but try to identify a particular vertex that you need to remove. So let me remove this. What do I get remaining? I now have a graph with how many vertices? N vertices. Is it connected? Why is it connected? Because what you removed was the leaf. So everything had a, there was a path before, there was a path now. Does it have cycles? No, because you have removed an edge. So if you're removing something, you cannot create cycles. So that's a tree. That's a tree over n vertices. So how many edges does it have? Minus 1. 1. So the total number of edges in this whole thing is n. Okay? So that's the idea, but there is some things we have to be precise about. So this is the tree that is given to you. Identify leaf, let's call it x. Okay? X has exactly one edge. Let t prime be t minus x. Okay? I'm writing this a little loosely, but what this means is I take the x and its edge out. I'm left with t prime. First observation, t prime has how many vertices? N vertices. T prime has no cycles because removing an edge does not form cycles. Okay? T prime has no cycles because it's part of T, and T has no cycles. T prime is connected. Why is that? The only edge we removed was connecting the leaf. So all paths that existed before still exist. So by induction hypothesis, T prime has how many edges? N minus 1. So how many edges does T have? N minus 1 plus the one edge that we have removed. Okay? There's one thing that is still incomplete. You have to do. Yes?
I have a question. So here we assume that the number of vertices will be greater than 3, and how we are we assuming that the base case is 1?
That number of vertices greater than or equal to 3 was for the definition of the cycle. A tree is well defined over two vertices also, just the edge between them is a tree. So a tree is completely well defined always. This way of writing for a cycle is only well defined. Okay, so everything looks good here except one part. What part do you think doesn't look good here?
Is it maybe that there are always leaves?
Exactly. I mean, I said identify a leaf. An intuitive leaf is obvious. Of course, tree has leaves. That's the whole point of trees, right? But why should a tree have a leaf? Okay, it's a philosophical question, but this is, in this case, in our definition, we have to argue that a tree has a leaf. How do you prove that a tree has a leaf?
Because it has no cycle.
What is the leaf, by the way? How do you define a leaf?
No, it's only one edge.
A node that has only one edge. Okay, so that's very clear. That will be fine. So a leaf is a vertex with exactly one edge. So how do you prove that? Because I've defined it, the definition of the tree has nothing about leaves, right? A tree is a connected graph with no cycles. Why should a tree have leaves? Somebody does not spoken before. Why should a tree have a leaf? Yeah.
You say if it has no leaves, then it's not a tree.
Well, why would it not be a tree? The only thing I know about a tree is it is a connected graph with no cycles. So if it doesn't have a leaf, how is it not a tree? The tree has to have two properties: connected, no cycles. If it has no leaves, then what do you think there would be? Or maybe not connected. Okay? Right? So let's try to prove that. Okay? So suppose a graph has no leaf. G has no leaf. We are going to prove that it cannot be a tree. Okay? Alright. So, how do you go about proving this? Do you have a... Yeah, go ahead.
By contradiction, we can say that suppose if a graph has no leaf, then by default every vertex will have more than one edges by definition of leaves.
Not necessary. Something could have also zero. Okay, but that's the easy
If
case.
it's zero, then it's not connected.
Excellent. Okay, so if a graph G has no leaf, there are two cases. There exists case one. There is a vertex with no edge. Then you agree that this graph is not even connected. If there is a vertex sitting there that has no edges, then this has there is actually notice that there is a slight problem, but you can only a tree with more than one vertex has a leaf, right? Why is that okay? Because remember, we were doing it not in the basis but in the step. In the step we are already talking about more than one vertex. Okay, so I should suppose a graph G with at least two vertices has no leaf. That means there is a vertex with no edge. If there is a vertex with no edge, then that vertex is disconnected from the rest. Implies G not connected, so it's not a tree. If a graph is not connected, it can't be a tree. What's the second case? There is no vertex with no edge. That means every vertex has degree At least 2. Because we are in the situation where there is no leaf. Every vertex has degree. Everybody understand the meaning of degree? Degree is just the number of edges adjacent to the vertex. Okay. So in this case, what would we like to do? Find the cycle. How do you find the cycle?
Assume that the graph has only 2 nodes, so and if the degree is 2, one will go into this and it will give it has a cycle, which contradicts our assumption that it is a.
No, but that's for 2 nodes. But in general, the graph could have lots of nodes, lots of vertices. I want to prove that if you give me a graph, no matter how big, in which every vertex has degree at least 2, why should it have a cycle? Yeah.
We start progression from certain node,
Yeah.
and every next time we take a different node.
Yeah.
And we keep doing this.
Yeah.
Graph has n vertices.
Yeah.
After we exhaust at least n steps,
Yeah.
we will have to repeat.
Excellent. Okay, so this is a slightly different argument than what we have seen. But the point is this: pick any vertex. Okay, start from any vertex. Let me call it V1. Start from any vertex V1. We know that it has 2 edges. Okay, I just pick any one of the edges. Okay, and pick any one of the edges and go to P2. Any one of the, how many ever edges it has. V2 has at least 2 edges. So I pick an edge different from the one that I came in. I can always do that, right? Agree? Go to V3. V3 has at least 2 edges. And I can pick one of the edges that is inside. And I keep going. So this graph is a finite graph. There are only n vertices in this graph. So every time we are arriving at a vertex with some edge and leaving the vertex from a different edge, and we can always do it as long as we don't visit the vertex again. So this will keep on going, but at some point something should happen. It cannot keep, every time it cannot discover a new vertex because there are only n vertices, so it has to stop at some time. And as far as we have indicated, it can never stop. The only point at which it can stop is if it comes back to something that we have already seen, because otherwise we can keep on going. But it has to stop in n steps. You can't keep on going forever because there are only n. So no matter where you start off from, you will be able to come back to it. And that's the cycle. Yes?
There will also be the case where there is no cycle, but there are parallel edges.
No, so there are no parallel edges in this graph.
That will,
Yeah, I think throughout we'll assume, unless otherwise mentioned, no parallel edges. A parallel edge is when 2 vertices have many edges between them. Okay, we are just assuming that if there is an edge, there is only one edge between. Okay. Yes.
In this case, V1 is a leaf node.
Not necessarily. No, there are no leaf nodes, right? So V1 has other things as well. I started from V1 just because I wanted to pick some vertex, and then I kept walking. And all I'm saying is, if I don't reach a vertex again, then I will keep on walking. And I can keep on walking for only n steps. So at some point, I have to revisit a vertex. The moment I revisit a vertex, I find a cycle. Okay? That cycle may not include V1. The cycle that I found may not include V1. Okay? Yeah.
so I still have a question about that. So 2 questions. One is what he said is that we are assuming that for every graph that has more than 2 vertices,
and it has no leaf.
yeah, and that it has no leaf.
No. We are saying if a graph has at least 2 vertices and no leaf, then it has a cycle.
No, so what I am asking is that what we said, that suppose if we prove that for a graph with 2 vertices, there has to be a cycle.
Graph with 2 vertices,
With more than
2 vertices and has no leaf.
Yeah, so
Yeah.
for that, because
But for 2 vertices, the graph has to have a leaf. So for 2, you cannot prove it. There is no graph with at least 2 vertices and no leaf. Right?
but if they have multiple, if they have 2 edges incident on them,
You mean what you're talking about this? This is not allowed. This is parallel edges.
So,
Okay, so with 2, this is not. Yeah.
so if it is allowed, is that a circle?
That's I don't. You have to have good definitions for it and so on. Yeah. Technically, yes, that's a cycle.
and why can we assume that there can't be parallel edges?
Why can we assume? No, that's our definition. We have defined a graph in which we don't. The problem with the other edges are not complicated to deal with. It's just we have to then differentiate between this edge and this edge. Well, I'm using the same notation to write both of them, and so we have to differentiate between them. We have to give labels to them and so on. And the definitions change. So here we are assuming we have put this edge to indicate a relationship. Then what does that other edge mean? That means it's a different relationship. Then we have to give meanings to these relationships that we are not talking.
So to make it concrete, shouldn't we assume both the cases that it has no parallel edges? So if we assume that it has no parallel edges,
No. That by definition we are talking about graphs with no parallel edges. Our definition of a graph is, our definition doesn't even allow us to talk about parallel edges. Okay? Meaning this picture is not allowed in our
but
context.
isn't that a valid graph?
It's not. Our
So we
definition
are defining that
This
a
is
graph
not-
with parallel edges is not.
does not exist. And there is a technical term for it. Graphs with parallel edges are actually often referred to as multigraphs. Okay, there is a different body of work associated with that. Graphs typically do not allow parallel edges. Just the normal definition of graphs. Yeah.
Can we use the definition of a cycle to prove that there is, because
Well, you have to show the existence of a cycle. So our goal is to show the existence of a cycle. So here, notice that we are using the definition in some sense because I'm showing the existence of a cycle by walking from V1 to V2 to V3 to V4 to V5 and so on. And then I say that at some point, this walk has to merge with itself, and then I will get the cycle as to the point where it merges. That sequence is the cycle.
so if we use the inverse of the definition of cycle, then we can prove that there will always exist a cycle. In case if the graph is connected and there exists more than n minus values.
Can you say that?
So if we use the inverse of the
What does that mean? What is the?
If a graph is connected
Yeah.
and has more than n minus 1 edges,
Yeah.
then it will have a cycle.
Yes.
So here we are assuming that every
But how do you prove that? In some sense, we are sort of proving it here, but not. It's sort of we are sort of proving it. This the same thing here. That a graph, if it is basically we are saying if a graph G has no leaf with at least 2 vertices, then it has a cycle. And then if it has a leaf and it is connected and does not have a cycle, then it has exactly n minus 1 edges. So if it has n edges, then it will have a cycle. So okay, so I'll move on. So everyone start from any vertex, and I'm not writing the argument down here. Implies cycle. So this means G is not a tree. Therefore, a tree always has a leaf. Therefore, whatever we did there, a tree with at least 2 vertices always has a leaf. A tree with at least 2 vertices always has a leaf. So the induction step was correct. So we are done. Yeah.
Could you also use at least the hypothesis that a tree can't have more than n-1 edges and show that if every vertex has 2 edges, then it will get past the level?
Well, the hypothesis was for n vertices, not for. We are working with a graph that has n plus 1 vertices. So I'm not sure you can use the hypothesis to do that. Okay. I mean, to some extent, we are proving this separately. We are proving this completely separately from the induction. Okay. So this is something we are doing this only to justify our first step, which was saying identify a leaf. Okay, but how do we know there is a leaf? This part argues that there is always a leaf. So now we can identify a leaf. Okay. So now let's, now that we have defined the tree, and it took us a little bit of time and discussion to do it, but now armed with the definition of the tree, we can talk about interesting trees we can look for within graphs. Okay. There is a kind of tree which is called breadth-first tree, BFS tree, okay, which is what we are going to build. And there is a tree associated with it, but there is a procedure. It's more a procedure which builds a tree, but let's define what breadth-first search is. So breadth-first search is simply an exploration of neighborhood around a given root node, given source. Okay? So let's suppose, and it's very easily described in just different examples. I'm just going to give you this example and you can review it. So let's say this is your source, S, and let me put some names here, A, B, C, D, E, F. You know, it's not a tree, it's just some graph. And we are trying to explore from S out. Okay? So what breadth-first search does is intuitively, it starts from a given source, looks at vertices within distance 1, puts them in layer 1, vertices within distance 2, puts them in layer 2, vertices within distance 3, puts them in layer 3. So it just does a sort of a layered process. So when I say distance, I mean the number of hops away. Okay. What does that mean? Well, remember that there are many different, possibly many different paths going from S to, let's say, something like F. There is this path, S from C to F. There is also this path, S from A to B to E to F. But the distance will be defined by the shortest path, shortest hop. So how do you build the BFS tree? So well, you start from S. Okay. You look at all of the edges around S. So you go to the adjacency list representation and look at all the edges going out of this. And write down all the vertices. Put them on, so put S on layer 0 and put all the neighbors of S on layer 1. Okay? And you have these edges to mark. Okay? Then you go through all the vertices in layer 1 and look at each of the edges from them. So how many edges does A have? 3. S, B, and F. So you look at the edge from A to S. Well, S is already in layer 0, so you let that alone. You look at the edge from A to B. You note that, oh, S is already in layer 1. You leave that alone. Then you look at the edge from A to F. That's new. We have discovered a new vertex. So you add F to layer 2. So that's it. Then you look at B. It has an edge to S. There is nothing to do. Edge to C. Edges to D, E, and that's it, right? Edges to D and E. So I put B, E. From C you have an S to S, edge to S, edge to B, we already marked that, edges to E and F. E is already discovered, so you don't add that again, you just mark. Note that you have discovered this edge. And C to F. Aha, thank you. F is already there. So you have not discovered it new, so you should just. Okay? Then what we are going through F, D, and E. F has an edge to A, already marked, edge to C, already marked, edge to E. Okay. D has an edge to B, already marked, the edge to E, and an edge to H, and edge to G. E has an edge to H, F marked, B is already marked. Okay. And finally, then you go through G and H. G has an edge to D, that's it. H has 2 edges to D. So that picture is the breadth first search traversal of the, starting from S. Okay. What does breadth first traversal do? It builds these layers L0, L1, L2, L3. Okay. So So breadth first search does a bunch of different things. It partitions the vertices into layers. what does layer Li consist of? Set of vertices that are I hops from the source S. Okay, that's the first observation. Second thing, it distinguishes between, it sort of classifies edges into two categories. Let's say, can you identify the edges that are being classified into two categories? One category were the solid edges, and the other category was the dotted edges. What is the difference between the two? So there are the edges, cross layer edges. What can you say about the cross layer edges? They only go between consecutive layers. You never have an edge going between layer Li and Li plus 2 or higher. Why is that?
We expand all of that node's edges on L1 itself, so we don't need to go to L3.
Right. So why would we never have, let's say, an edge from here to here? Why don't we have an edge from L1 to L3?
By definition, that node would be into L2.
Correct. By definition, this would have been an L2. Okay. So edges on cross layer edges only go from Li to Li plus 1. Okay. And then in layer edges, I'm just giving names myself. In layer edges are within a layer. Okay. Yes.
Why are we marking things twice or using in-layer edges at all?
Why are we? So this is, we will see its applications. It's helpful sometimes. It depends. We don't need to. A lot of work with graphs is trying to process them to gain some idea about how the graphs connectivity is. So this provides some useful information. Okay, but if you don't need it, then you won't mark it. Okay. So partitions vertices into layers. You can consider edges as two different groups, and you agree that. Okay. So I think that's enough for now. So first, immediate applications. Because it partitions vertices into layers, Li is set of vertices I hops from S. We immediately have shortest path from S to all vertices. Or certainly you find the distances immediately, right? So what is the distance of S to any vertex? Well, just look at the layer that vertex lies in. Okay? If you have to find the path, what do? There are several things we can do to find the path. One thing that is done is, let me draw the same picture. S, A, B, C, F, D, E, and then GH. We had this. And then we had this. Yeah, I'm only drawing the cross layer edges here. What you do is, as you build this, as you do the breadth first search, for every vertex, you keep track of one of the two vertices, one of the vertices from where it was reached. Okay, so I will mark this edge This is the edge that I first used to discover A. Then I will mark this, and then I will mark this. And in this example at least, I discovered F from A. It doesn't matter which one you choose, but let's say this is a, so I'll mark this. So for F, I will view A as the parent. Okay. For D, it has these aside from B, for E also from B. For G, it's E. So these, so this is the parent. So I say the parent of F is D, the parent is A, the parent of A is S. So this marking that I've done leads to a tree. This is the BFS tree. So if anybody talks about the BFS tree from particular source vertex S, this is exactly the BFS tree. Once you have the BFS tree, it's very easy to construct a path, right? What is the path from S to G? Well, start from G, look at its parent, its parent, its parent, eventually it reaches that is the path. Okay. So then the shortest path between any vertex V and S is basically is V to the parent of V to the parent of the parent of V. Okay. Pi is, I'm using it for the word parent, parent of V, parent of V, and so on until you reach S, which is the ultimate ancestor for everything. Okay? All right. Good. Now, let's look at two. So one other way that's very helpful is you can use BFS to describe connectivity. If you start your BFS from a source S, then by the time you end, what happens? You have reached all the vertices that are reachable from S. So if that's all the vertices in the entire graph, then you know the graph is connected. If that does not include some vertex that is supposed to be in the graph, that means S is disconnected from that vertex. So what BFS allows you to do is BFS from S discovers all vertices reachable or connected to it. Remember, when we say connected, it does not mean it has to have a direct edge. Connected means there is a path. Okay? So this is basically referred to as the connected component of S. But if in the graph there happen to be some other vertices, I, J, K, that had no connections to this, then we won't discover I, J, K. Okay? And if you have to discover them, then we'll have to pick some other vertex that we have not seen before, start a BFS from there, find its connected component. And then some other vertex that we have not seen before, do a BFS from there, find its component. But basically the point is that BFS, by running BFS repeatedly, you can find all the different connected components. Okay? Good. Before we look at our third application, which is of bipartite graphs, let's try to see how. I haven't given you the code here because it's fairly straightforward. But let's take the running. Let's try to analyze what the running time of BFS would be. Okay, so let's try to understand just how our procedure went. We started from source S. Somebody gave us this source S, so we started from this source S. What did we do? We went through all the edges of S and then added each of these to a layer. Now, how do you add them? Think of this as just, it's like a cube. So you add these vertices one at a time, and you put them in this. Then what did we do? We went through each of those vertices, looked at all of their edges, and if we found something new, we added them to the next layer. Okay. So what is the time? Well, so let's start from here. How much time did it take us to look at all of its neighbors? At most n. Okay? But a better bound would be its degree. Right? So the time taken to process this was degree of f. Okay? Then what did we do? We took the first vertex from this layer and we went through all of its edges. How long did that take? Sum of its degree. Then we pick the next vertex. We are just working through in a queue, so it does not. How much time did it take? Its degree. And through this, its degree. Kept on going, its degree, until we have exhausted everybody. And then we don't find any more vertices and we stop. So it took us the sum of all the degrees of the vertices that we have seen. If we want to do connected components, then at that point we know some vertices that we have visited, some vertices that we have not visited. We pick another vertex and we repeat. Okay? Good. So basically the running time for BFS remember, we have to keep track of, for every vertex, we have to look at least once, right? It might have no edges, for example. It might be by itself. We still have to look at it. So we have to look at every vertex at least once. Then we have to look at the sum of the degrees of all the vertices. Because you have to go through every single edge. What is the sum of the degrees of all the vertices? The edges, it's actually twice the number of edges because every edge is being looked at twice, once for each of its neighbors. So the sum of the degrees of all the vertices is exactly equal to 2m. Does people see that? Every edge appears exactly twice. And we are looking at every edge twice, right? Once we discover this vertex, and then once we look back, even these edges, we once look for D, once we look for E. So the running time of this procedure is big O of n plus n. And this n is the number of vertices, m is the number of edges. This is what is referred to as linear time. Because, why is it linear time? Because remember, the graph is given to us in the form of an adjacency list. What is the size of the adjacency list? N plus an entry for every edge, actually 2 entries for every edge, so n plus n. Okay? So it is linear in the size of the representation. So whenever somebody says, give a linear time algorithm for this graph problem, what they are trying to ask you for is to give a linear time algorithm, give a time algorithm that runs in time big O of n plus n. There are two parameters here. For the most part, m is bigger than n. Because if m is smaller than n, we know it's a tree or disconnected. So that's what it's most of the time. So this is really the dominant part, but it's always good to write. Okay? Is that clear? Good. Okay, so let's look at the one more application of breadth first search. Bypass. It's a nice application. So, what's a bipartite graph? A graph is said to be bipartite if its vertices can be split into two parts, such that all the edges go from one side to the other. There are no edges within side. Right? So you need not have the same number of vertices on both sides. So this is an example of a bipartite graph, because I can split the graph into two parts. One could be called red, the other could be called blue. So I can color the graph into two parts, red vertices and blue vertices. All the edges go between a red and a blue vertex. You never have a red edge or a blue edge. Can split the set B into A union B such that every edge is one edge UV where U belongs to A and belongs to A. Okay, there are many different ways of defining it. It's also sometimes referred to as two-colorable, because you can think of as the vertices of A to be the red vertex, vertices of B to be blue, and you're trying to make sure there are no edges within red. Okay? Now, so that's a bipartite graph. Examples of there are lots of applications of bipartite graphs. Like this, you can think of the stable marriage problem, some definition where men on this side are hospitals on one side, students on the other side, and the edges maybe represent those hospitals that are willing to take those students, something like that, some version of that. You can think of these as machines, the other set as jobs. You have to assign jobs to machines. So it's only meaningful about talking about assigning jobs to machines, not jobs to jobs or machines to machines. You'll see when we come to do network flows, you will see many examples of bipartite graphs coming up where we are trying to match one set of entities with another set. Okay? Okay, so here is the question. I give you a graph. So the problem we are trying to solve is I give you, let's say G is a graph, and let's assume it's connected. Okay, just for our purposes, to make our life a little simpler. So G is a connected graph, and our question is G bipartite? Okay. Is the question clear? So I give you a graph in its adjacency list form. So I give you all the vertices, I give you all the edges in an adjacency list form. I would like you to determine, is this graph bipartite?
Is there cycles?
Good question. So let's take the simplest example. Let's suppose the graph was a tree. Is the tree bipartite?
Yes.
Okay. Why is that?
There are no edges between the same there.
What is, so how will you, so to show that the graph is bipartite, you will have to split the vertices into two parts. How will you split the vertices into two parts in a tree? Yep.
You can apply BFS.
So for a tree, okay, yeah, you can apply, you're applying BFS to the tree.
Yeah.
Okay.
And then we take all the odd layers and the even layers and split.
Good. So if you look at the tree, put any root source, sort of imagine you root the tree, right? Anything that's at an odd level, you put them as red. Anything that's at an even level, you put them as blue. Okay? You agree there are no edges on the same level of a tree. It's pictorially it seems correct. Why don't we do the same thing for any graph? Okay? So here is what we do. You give me any graph, G. I want to find out whether it's bipartite. So I pick any vertex S, and I do a BFS from S. I get my vertices in layer 0, so this is layer 0. Get my vertices in layer 1. Get my vertices in layer 2. Get my vertices in layer 3, and so on. Keep on going. Okay. So I keep on going, and by the end I would have discovered every vertex, right? Why is that? Because I assume that the graph is connected. I'm going to find out every single vertex. I have to find out whether it is bipartite or not. How do I tell whether it's bipartite or not? Yeah.
I just have a question.
Yeah.
If you do BFS on a graph,
Yeah.
you're in this version, you're ignoring the edges that connect two nodes in the same way.
No, you never ignore. You never ignore.
Yeah.
BFS identifies, so it is marking.
So then you're not, when you do this, then now if you were to separate these like the odd and even, like I said before,
Excellent.
you're gonna have connected edges in each group.
Absolutely right.
So
Absolutely right. Absolutely correct. So let's say I run the BFS and this is what the picture looks like. Okay. I can try the suggestion that was made, separating things odd into even. Think of these as the even ones as red and the odd ones as blue. But that's a problem, right? Why is there a problem? This edge. Yeah.
So, question, for in the second level and the third node over, one more, is there a reason why?
It's no. There is. It cannot lie hanging like that. It has to have a parent. Good. So you agree that if I say that this is bipartite, this is my the odd ones are my blue and the even ones are my red. That's not bipartite. Yeah, but here is a nice claim we're going to make. If I run BFS, if I ever find an edge like this, it cannot be bipartite. If I never find an edge like this, then you agree that I have a bipartite thing? Yes.
You can have any connections between odd layers, not just the same layer.
Well, notice that there are no, in the BFS, there are no edges jumping levels. So that problem is not there.
You made it single.
That's a good point, very good. Yeah. So notice that I never have to worry about an odd L1 to another odd, right? Because that is not there by definition in the BFS. But I do have to worry about these edges. And our claim is that if these edges are there, it cannot be bipartite. We have to prove it. If these edges are not there, it will never be bipartite. If these edges are not there, then I'm done. Okay? So here's the algorithm. Run BFS from any vertex. I picked an arbitrary vertex S. If there exists any edge within a level, within a layer, return not bipartite. Else, return bipartite. And usually when you say something is bipartite, you have to give proof of it. So a proof is going to be the red vertices are the odd levels, odd layer vertices, blue vertices. Okay? See, it's a very simple algorithm. So this is the power of just using things that we have. So, and this is how we will often write algorithms. Okay? Let's, before proving that it's even correct, let's try to understand a few things about it. So we are running BFS from S, that's linear time. We are marking each of the edges. This is one of the reasons we are marking. So we can keep track of whether we ever see a dotted edge. If we ever see a dotted edge, we are going to say no. That's easy. If we do not see a dotted edge, then we are going to return bipartite. We already have our odd layers and even layers. So the whole running time is clearly order n plus n. Yes?
So are we saying that you can only create bipartite graphs from trees? Is that what we're trying to get at?
If you were to start, no. You can create bipartite graphs from, give me a simplest example of a bipartite graph that is not a tree. A cycle with? Cycle with 3 nodes. It's a very good example. This is bipartite. It's not bipartite. Why is it not bipartite? Well, let's let the BFS from here. What do we get? Layer 0, layer 1, if there's an in between them.
Square.
Yeah.
Good. This is bipartite. Not a tree. This is bipartite. Okay? Let's go on a little bit. What about pentagon? Is it bipartite?
No.
Yes or no?
No.
No. Hexagon.
Yeah.
So what pattern do you see? Even cycles are bipartite. Odd cycles are not bipartite. In fact, that is exactly bipartite graph is. The graph is bipartite if and only if it has no odd cycles. The moment it has an odd cycle, it's not bipartite. Yes?
Why is this square?
Why is square a bipartite graph? Good question. How will you split your red and blue? So this you can say is red, this is red, this is blue. Okay. Okay. So let's connect this cycle business. G is bipartite even only if it has no odd cycles. Okay? Proof. Let's go in one direction. Let's suppose G is bipartite. We now want to prove that there are no odd cycles. What does it mean? The G is bipartite. That means there are red vertices and blue vertices, so that all edges go between red and blue, and so on. There could be lots and lots of this. We'll have to prove that it has no odd cycles. To prove no odd cycles. How do you prove it has no odd cycles? Well, something like this. It's often to prove that it has no odd cycles. It's easier to start with a given an odd cycle, derive a contradiction. Okay? So we'll prove by contradiction. Suppose there was an odd cycle. See, and we have already seen that from that picture, triangle, hexagon, we are getting this idea. So suppose you gave me an odd cycle. So the odd cycle consisted of V1. Notice that it has to have any cycle has to have at least 3 vertices. So it consisted of V1, V2, V3, V4, until some odd number, V2k plus 1, back to V1. This was the odd cycle. Okay. We'll have to argue that this just cannot happen. How will we prove this? So this is a contradiction. Okay, remember, there is a coloring business going on, right? So let's start with B1. What do you want with color?
Okay.
Let's say red. If this is red, then this is blue. This is blue, then this is red. So every odd one should be red, every even should be blue. That means this one should be, and that's a contradiction. So an odd cycle cannot exist. See that? Good. That's this direction. Let's do the other direction. The other direction, interestingly, we'll use our breadth search. Suppose no odd cycle. Then, what we are going to argue, if there is no odd cycle, then when we run BFS, we are never going to have an in-layer edge. Okay? Suppose no odd cycle. We run BFS. So suppose no odd cycle. Run BFS from some vertex S. And we get layer 1, layer 2, layer 3, and so on. We are going to argue run BFS from S will show no in-layer edge. Why are we done if we argue there is no in-layer edge? Because if there is no in-layer edge, then we can call all the odd layers red and even layers blue, and that would be a bipartite separation. Okay? So will show no inner edge, which would imply bipartite because odd could be red, even could be blue. So all that remains us to show is that there is no in-layer edge. How do we prove that there is no in-layer edge? Again by contradiction. Suppose there was an in-layer edge. Okay? So it could be in any layer. Let me pick this layer, and here are two vertices that have an in-layer edge. So what do I have to? It should contradict something. What should it contradict? What was our assumption? There is no odd cycle. So somehow from this in-layer edge we'll have to construct an odd cycle. How do we do that? How do you think we should do that? Notice that this is a long BFS, it's buried somewhere here. How do you build an odd cycle?
In order to find the
Well,
Both should be going to the same node.
good. So you sort of try to see, remember we are keeping track of these parents, for example. So we could just go back to the parents. So you start from here, go to its parent, which is in the previous layer. Then go to the grandparent. At some point, these two have to meet. Why? Because eventually it's going to meet here. Either it meets before or it meets there. Doesn't matter. It's going to meet somewhere. So let's say it meets here. It's very clear that this is a cycle. Everybody see that? Why is this an odd cycle? Well, there are two vertices in every layer except here. So the number of vertices in this cycle is odd. Right? Each of them has a different parent. Each of those parents has a different parent. Each of those parents has a different parent. At some point they have the same parent. So the number of vertices in this whole cycle is odd because it's even, and then there is no extra. In-layer edge implies cycle. Okay? Any questions? Okay, so that's good. So what we have seen is that the search, it runs in linear time. It can be used to determine whether the graph is connected. It can use to find all the connected components of the graph in linear time. It can be used to find shortest paths. When I mean by shortest, I mean number of hops. Okay, later on we are going to study more sophisticated algorithms for shortest paths where there are weights on edges. Here we are assuming there are no weights or anything, no distances, it's just one hop. And it can be used to find out whether a graph is bipartite, but there are lots and lots of other applications that we'll also see. So, so far, I'll just say a couple of other things. So far, we have assumed that the graph is undirected. We can apply BFS to directed graphs as well. Using exactly the same idea. Connectivity is more complicated for directed graphs, so let's not get into that. Shortest paths, the same idea works. Okay, it can be used in linear time. Find shortest minimum of path from source to all vertices reachable from. Okay? The notion of bipartite is only defined for undirected. Okay? You can probably define some notion of bipartiteness for directed graphs too, but typically we don't work with that. It's only for undirected. Okay. For directed graphs, another, so we are going to switch gears a little bit to directed graphs, and I will start by talking a little bit about depth first search, and I think we won't be able to do much more on that today. But for certain applications of directed graphs, for certain problems in directed graphs, depth first search seems more suitable. But let's try to understand the idea of depth first search is sort of another way of traversing the graph, except instead of going layer by layer, you go deep and then you come back and deep and come back. So you sort of go explore in depth and then backtrack. Okay, you explore in depth and then backtrack. I'm going to describe depth first search for directed graphs. Using a simple example. And again, you're doing it from a particular source vertex. A, B, C, D. So the idea here is that we again explore, but rather than putting everything within distance 1 first in the queue and then going through each of them, then distance 2, we will pick the first thing that we see and start exploring in depth, and then the first thing that we see, so keep going deep, and then if need be we'll backtrack, and then we keep going deep and backtrack. Okay? So and the way, one nice way to keep track of it is to keep track of time. And at each point, figure out where we are in the graph. Okay? So we will keep track of two things. We will keep track of a time that a vertex was discovered, discovery time, and the time when a vertex is finished, in the sense that you've explored everything possible out of there. And let's call that finished. Okay? So things that we're keeping track of: discovery time, finish time. As always, you'll keep track of your parent. Where do you first arrive from? Okay? Okay, so we'll start from S, our source. So we discovered a time 0. So the first thing I'm going to write down is this discovery time 0. I will look at, I'm going to explore the edges out of S. So I'm going to look at the first edge out of S. Pick any one, A or B, it doesn't matter what order it's given in the adjacency list. So let's say it's A. when I come to A, is this the first time I'm seeing A? So I make a note that I discovered A at time 1. I plot a stick 1, I discovered A at time 1. And this is the edge that led me to the discovery. Okay. Good. Now from A, I'm going to look at edges going out. Okay. How many edges are going out from A? 2, B and E. You can pick any one of them. You want to pick? Let's say E. So then we come here. This is the first time we're discovering E? Yes. So at time 2, we have discovered E. Then at time 3, we discovered I. Now I has no edges going out. So we look at this adjacency list and we find it's empty. So we are done with that. So at time 4, we are done with that. And we go back to experiment. Okay, then we look at E. Have we explored all edges out of E? Yes. So we say, all right, we are done with E. So at time 5, we are done with E. Go back to A. Go back to the parent F. From A, what are the edges? A to B. So we go to, this is the first time we are discovering, A to B, and its discovery time is 6. Notice that we could have discovered B from S itself, or from A. So depending upon what we do, we could get different times, but let's keep on going. So from B, we look at edges going out. B has an edge going to D, so we get 7. D has an edge going out to H, to C. Let's go here. 8. C has an edge going to B. But we've already seen B before. Okay, so you could mark this edge in a different way, but let's leave it aside. We don't have a pen, so let me just progress here. So C, you look at B, there's nothing more to do because B has already been discovered. So you go to C to G, and this is 9. You go G to F, 10. F has an edge to A, we've already seen it. F has an edge to I, we've already seen it. So F has an edge to J. So we see that. J has nothing going out other than 1 to G, we've already seen it. So we are done with J. Goes back to F. Done with F. 15. Goes back to G. Done with G. 14. Goes back to C, done with C, 15, goes back to D. Is D done? No, because there's H. We discover H. 16. H has an edge to K. 17. K's edge to J is already discovered. 18. Go back. 19. Go back. 20, go back, 1. That's where it ends. Did I pick everything? So the one thing to note here is that these squiggly edges form a tree, and that's exactly what is called a DFS tree. We'll talk more about the DFS tree and all the other edges in the next class. So I'll see you later this evening.